This video is an introduction to area by double integration. We have already determined that the double integral over R of f of xy dA will determine the volume under the surface f of xy over the region R. Consider if we let f of xy equal 1. This would mean that the height at every point in the region would be 1. In essence, this would find the area of the region R, because volume is base times height. The area of a closed, bounded plane region R is A equals the double integral over R of dA. So in essence, we're letting f of xy equal 1. Remember that dA can either be dx dy or dy dx. Example, sketch the region bounded by the given equations. Express the region's area as an iterated double integral and evaluate the integral to find the area. We're given the curves y equals the fourth root of x and the square root of y equals x. Now our first step is to graph the two equations in the xy plane and get a sense of what our region will look like. So I have my xy axes, and my first equation is y equals the fourth root of x. I know that's going to go through the point 0, 0 and 1, 1, and it's going to look similar to the square root, y equals square root of x, but it will be a little flatter. Next, we're going to graph square root of y equals x. So I know square root of y equals x is the same as y equals x squared with x greater than or equal to 0. I just get that by squaring both sides, and because x is equal to a positive square root, I know that x has to be greater than or equal to 0. So I know this is the right half of the parabola y equals x squared. It goes through the point 0, 0 and 1, 1. And so I have y equals x squared graphed accordingly. Now the region I'm trying to find the area of is the region between those two curves. So I'm going to shade that in on my graph. And now I want to set up a double integral. So I know that y goes from y equals x squared on the bottom of the region to y equals x to the 1/4 on the top of the region. Since y has function bounds, x must have constant bounds. Remember in previous videos we emphasized that your outer integral has to be constants, otherwise you will not end up with a constant as your answer. So our smallest x, if we look at our region, is 0, and our largest x is 1. So the area is equal to the integral from 0 to 1. Remember, constant bounds are on the outside. And then the integral from x squared to x to the 1/4 of 1, because we're finding an area, so we let our function height equal 1 everywhere. dy, since my inner bounds are with respect to y equals a function of x, and then dx, because my outer bounds on the outer integral are in terms of x. Now I just evaluate. So I get the integral from 0 to 1 of x to the 1/4 minus x squared times dx. Notice that because my integrand was 1, I just get the upper bound minus the lower bound as my evaluated integral. So now I do the outer integral from 0 to 1. So I have 4/5 x to the 5/4 minus 1/3 x cubed evaluated from 0 to 1. And if I plugged in my upper bound and then plugged in my lower bound and subtracted, I would get 7/15. And so we found that the area of the region between those two curves is 7/15. So that's all there is to finding area using double integration, is you find your bounds just like you did in the previous sections, and then you let your function equal 1.